very much for this invitation. I will talk about the project joined with Krzysztof from the University of Warsaw and Adam Spiewak from IMPAN, from the Institute of Mathematics of the Polish Academy of Sciences. And we have been working on this for several years. We have published 4 articles and one preprint that I hope will appear this year, and we are continuing to work on it. This talk is based on more or less 3 papers, and the title is Prediction and Reconstruction of Dynamical Systems, a Mathematical Point of View. So to fix an example, what I mean, we will consider the Lorentz attractor. So in the 60s, Lorentz, who was trying to model the weather, let's say, he was working in meteorology, he came up with quite simple baby model, which you can see it was a system of ODEs. He didn't have the computers we have today. He was not able to draw this beautiful attractor, but he realized he came upon something very interesting. So this fractal, this attractor that this system possesses has many interesting features. One of them that became very famous is that it's very sensitive to initial conditions, so sometimes people refer to this discovery as the birth of chaos theory. But in any case, we will just use this as an illustration of a system that we are measuring in the laboratory. So we are doing some experiment. It turns out it's the Lorentz attractor, but we don't know that yet. So we want to measure some quantities related to the system. This is usually referred to as observables. And we would like to reconstruct the system. And oftentimes it happens that you cannot really measure many independent variables. Usually you have only a few. So let us concentrate on the case that you have only one significant observable. Let's say it can be the temperature, the pressure, I don't know. It depends on the experiment. And the question that Takens asked himself was, okay, let's say I have one observable, can I still reconstruct the system? And then he came up with the following idea. It's called the time-delayed measurements. This has already appeared several times in this conference. So XT will be a dynamical system. So we only consider X to be compact. T, in this case, is a homeomorphism, but you will see that it can be, we can also weaken that sometimes. But in any case, we will think about the transformation T as the evolution of the system after a certain unit of time. Of course, this theory makes sense also in the continuous settings, but most of this talk we will talk about the discrete setting. So we have this observable, H, it's a function from X to R, and on the left-hand side you see the phase space, and we are measuring the function H along an orbit that starts with P, then TP, T square P, and you see we are drawing the, or noting the values of H. And the idea of Takens was, let's group these. So in this case, we take a window length of 3, HP, HTP, H, T square P, and we will plot this as one point, and then we will take this sliding window of length 3 and move it, and again plot, and so on. And his idea was that this can reconstruct the system. So let's see if this idea works in our example. So in the left-hand plate, you see the Lorentz attractor embedded in the 3-dimensional Euclidean space. And on the upper right-hand plate, we are measuring an observable, a very specific observable. This is, we take some orbit, and we are measuring the value of x, so one of the coordinates of the Euclidean space as a function of time. Then we are choosing a discretization parameter, which is called here big T, and we are plotting the graph x of small t, comma x small t minus big T, comma x of small t minus 2 big T. And the result is presented in the lower plate. And I hope this convinces you quantitatively that it seems to work. It seems to reconstruct the original system. So here is the Takens theorem. So I want to emphasize that Takens theorem is a mathematical theorem that is used as a justification for for a certain experimental procedure. So of course there are differences between the theory and the practice, and we will touch on that. So let's first see what the mathematical theorem says. So let me read it. Let M be a compact, this is the original theorem. Let M be a compact manifold of dimension D for pairs H, T, where T is a C2 diffeomorphism from M to M, and H is a C2 function observable. It is a generic property that the 2D plus 1 delay map, x goes to hx, htx up to ht to the power 2dx is a C2 embedding. So I need to explain here. First of all, I didn't define what Takens meant by generic. This is actually in the framework of the Bara category theory. For now, let's think about it as some framework of perturbation. So we are given our initial system that is given by the initial dynamics and the initial observable. And the idea is that in some sense for almost every perturbation of these values, this result will be correct. The second thing that we notice here is the length of the window. So according to the theorem, if you have a manifold of dimension D and you want to reconstruct it, you need to take a delay of length 2D plus 1. So this theorem became very popular. It's, this procedure has become very popular. It is widely used. The paper itself has been cited thousands of times. Now, obviously, returning to what I said before, in reality, the point of this theorem is that if you are able to plot for every x, for every state in your system, these vectors, then you get a reconstruction. And what I would like to emphasize that, of course, in reality, we are not able to do that. We are able to plot these vectors for, at most, a finite number of finite chunks of orbits, right? So we need to keep this in mind, that there is this difference. Another criticism that you can criticize this theorem is that it assumes that your system is on a manifold. And even in the example that we saw in the Lorentz attractor, it's obviously not a manifold, it's a fractal. And in many cases, you can have a system that is low dimensional, but if you try to embed it in a manifold or in Euclidean space, in a sensible way, then the dimension grows, or even it can happen that your original representation of the system is such that you have a very high dimensional space where a low dimensional attractor lives, and you are only interested in the low dimensional attractor. So it's obvious that you would like to give a theorem where the dimension is of the system and not of the surrounding manifold. And this is possible. About 10 years ago, I published something called the topological Takens theorem. Without going into the details, the dimension there is the dimension of the system, so of the, let's say, of the attractor. The second very interesting question is, why 2D plus 1? Why twice the dimension? Is this optimal? Can this be improved? So first of all, let us address the question, why twice the dimension? So this phenomenon is actually known to us from classical topology. So here is an exercise, at least I got this exercise in my first year, so I think many people got this exercise. And the exercise is the following. You consider the K5, the graph, the full graph on 5 points. Sometimes they give names to these points, I don't remember, gas station, house. And the exercise is to draw it in the plane without self-intersections. And it turns out this is impossible. So even though K5 is, and of course the picture here is not a solution of the exercise, because you can see that there are there are several self-intersections. So this is, from a topological point of view, this is a one-dimensional object, but you can prove that if you want to embed it in Euclidean space, you need at least 3 dimensions. So you have here this doubling phenomenon, and this is a particular case of something which is called the Menger-Nöbeling theorem, which says the following: if X is a metrizable compact space whose Lebesgue covering dimension is n, then there exists an embedding from X into the 2n plus 1 dimensional Euclidean space, and this result is sharp. So there is a family of counterexamples for every n which shows you that you cannot improve upon this theorem. So it seems that this doubling effect that we get in the Haken's theorem is justified. However, you can argue that oftentimes the experimentalist doesn't access all possible initial states. So in many experimental settings, actually there is some mechanism of randomization in order to choose the states, the initial states on which you will do your measurements. So you can maybe argue that there is either an explicit or implicit probability measure which governs which states one can see. And this is exactly the point of view that we will take. And then, before I state our first theorem, we will have to switch to another kind of dimension, the Hausdorff dimension, which is maybe the most popular dimension that you use when you work with fractals and with measures on fractals. So I'm sure you are familiar with this, but let me just review it shortly. So the S-dimensional outer Hausdorff measure of a set in n-dimensional Euclidean space is defined in the following way. You are so you are covering your X by countable covered by balls, and you fix some epsilon, and you want all the radii to be smaller than epsilon, and you are trying to minimize the quantity sum epsilon is. You do it for every epsilon, and the limit exists, you take the limit. And typically what you will see is that if you plot now this value as a function of S, first you will see infinity, then there will be some critical value where this value can take any value, and then you will get 0. And exactly at this critical value, this is what we will call the Hausdorff dimension. So this is formally the definition that is given here. And because we will work with measures, we want also to define what is the Hausdorff dimension of a measure. So this is very simple. We just consider the Hausdorff dimensions of all sets with full measure. In our case, all measures will be probability measures, so we will take all the sets whose measure is 1, and we'll take the infimum of their Hausdorff dimension, and this will be called the Hausdorff dimension of the measure. Okay, so now I can state the probabilistic Takens theorem, which was the starting point of our project. So we have X in Rn, it's just a Borel set. So a very general set. And we have some probability measure mu. We have the dynamics T going from X to X. This is given by an injective Lipschitz map. And notice we don't assume that the measure is T invariant. It's any probability measure. And we assume, this is the key assumption, that the Hausdorff dimension of the measure is strictly less than D. We have also some assumption on periodic points of lower period. I will not read it. This is, let's say, secondary, even though it's necessary. We have H, which is our Lipschitz function, which we think about as our observable. And we have a fixed collection of polynomials of n variables living in our space Rn. Again, here it says it's a basis of space, but this is also secondary, which exactly these polynomials are. And here comes the statement. We consider now polynomial perturbation of our original observable H in the following way. H plus sum, and now we have a vector of weights, alpha j, and we weight each one of these polynomials according to the weight. So the perturbation is given by the vector of weights, and obviously you can, if you want, you can imagine that these weights are really small. It doesn't matter, because the statement says that for Lebesgue, almost every vector of weights, so for almost every perturbation, you can find a Borel set X alpha, which depends on this vector, of full measure, such that the D delay map is 1-to-1 on X alpha. So the D delay map is this map H alpha X, H alpha Tx, and it stops at T to the power D minus 1X. So the point of this theorem is that you can go down from twice the dimension to the dimension in a certain probabilistic point of view. It's also very interesting that the perturbation is smooth. It's a polynomial. It's the best perturbation you can think about. And what is interesting with this, and the key dimensional quantity that appears here is the Hausdorff dimension of this measure. And such indication that you don't need twice the dimension is mentioned in the literature. So you can find articles where people say, we know that the Takens theorem tells us that we need twice, that the delay window needs to be twice the dimension, but we found out that it works when it's about the dimension. So maybe this can be thought as an explanation of this phenomenon. Actually, if you think about it, the example that I gave, so the example of the Lorentz attractor is such an example, because it turns out that the Hausdorff dimension of the Lorentz attractor is about 2.06. So according to the Takens philosophy, you will need a delay length, a window of length 5, right? It needs to be more than twice the dimension. However, we saw that we only need 3, so the dimension, because the D must be an integer, obviously. So this was, as I said, our starting point. But okay, so, and we started having, we started talking with physicists, and this is how our project continued. But before I talk about that, let me maybe mention or address another, I think, natural question, which is the Hausdorff dimension of the measure the fundamental quantity of this problem? I mean, just as we improved the original Takens theorem in this setting, maybe you can go even you can even improve it to a better theorem, or maybe another dimensional quantity that will be more useful. So actually, recently, we were able to prove that it is the correct dimensional quantity. We call this the reconstruction threshold theorem. Here we need to assume a little bit more in our setting. So we assume that X is a compact set, T is a Lipschitz map, mu is an invariant probability measure with respect to T, and let's assume now that the Hausdorff dimension of mu is strictly bigger than T. We fix some observable h from Rn to R. We fix the same family of polynomials. We consider again the same polynomial perturbation with this vector of weights. And the theorem tells that there does not exist a Borel set of full mu measures such that the D delay map is 1-to-1. So when the Hausdorff dimension of mu was strictly less than D, there is for almost every alpha, and when it's strictly bigger than D, for almost every alpha, there isn't. So I think this is a good indication that this is the fundamental quantity of the problem. Of course, you can ask what happens when it equals exactly D. In that case, you can find examples that are either one of the cases. This is many times we have this phenomenon in mathematics. Okay, so now let me connect this to physics. So when we, after we proved this and we talked with physicists, we got the suggestion that this may be related to some open conjectures. So specifically, these were conjectures published by Schroer, Sauer, Ott, and Yorke in 1998 in Physical Review Letters. And maybe connecting it to the previous talk, these conjectures were on the basis of simulations of certain examples. So this is a classical example of somebody making simulation, somebody very smart, somebody conjecturing something on the basis, and it turns out, as we will see, that they were right. I also want to point out the title of this article because it's also will be important. So it's Predicting Chaos Most of the Time from Embeddings with Self-Intersections. So from a mathematical point of view, it's a little bit strange to say that an embedding has self-intersection. But what they actually mean is actually the phenomenon that we saw in the probabilistic Takens theorem. Because the probabilistic Takens theorem tells you that on a set of full measure, it's 1-to-1. But if you consider the map on the whole space, this self-intersection might appear, of course. The point is just that, or maybe the surprising fact is that there is a set of full measure where you don't see self-intersection. Okay, so so this paper, which is a very short paper, it contains some results of simulations, and this contains two conjectures, and the second conjecture has several cases. So I will now describe to you the conjectures and what we were able to prove. And this will, I will have to give some background, especially about the notion of prediction, because the notion of prediction which they use in the paper is not straightforward. And in order to understand it, we will return to something which is called the Farmer-Sidorovich prediction algorithm, and then I think it will be clear what they meant. So the setup of the Farmer and Sidorovich prediction algorithm is the following. You have some ergodic measure-preserving system, you have an observable, Borel observable, and you have a point which is generic with respect to this measure. So it visits the space according to the measure. So if you will measure, if you will take the observable on such a point, you are in good shape. You didn't happen to fall on a non-significant, let's say, fixed point. So the input sequence, just as we have already discussed, is the measurements on some orbit. And here I enumerate this orbit. I start with h of x up to Tn plus k minus 1 for some k and n. So k is the important parameter here because this is going to be the delay length. So the window length which determines how I plot my vectors. So this defines a sequence z0 to zn of k delay coordinate vectors, which are defined in the following way. Zi is just hti up to hti plus k minus 1 x, right? So this is the sliding window of length k. And now I fix a y on what I called before the reconstruction space. So this is the space where I plot the vectors. Now let's call it the modeling space, because we are now talking about prediction, not necessarily reconstruction. And this y is not some arbitrary y, it actually needs to belong to this set. This will become clear now in the assumptions I will make. So I want to predict the one-step future of y. So in some sense, I want to take my modeling space and not see it only as a model of my original space. I also want a model of my dynamics. Because if I can do that, I will be able to make predictions. Can I do it? We will discuss it. But for now, let's assume we can do it. And the Farmer and Sidorovich algorithm is a very simple algorithm that says the following. Let's fix some parameter epsilon, a small parameter, and let's consider all zi, where you see I consider I strictly less than n. So these are zi's that have a future. Their future is zi plus 1. So I consider all zi which are in a small epsilon ball around y, and I say that my epsilon estimate for the future of y is just very simple. It's the average of the futures inside the ball. And so here you see I assumed that this set is non-empty. So let's summarize it. I think even I wrote it several times. Predict the one-step future of y by averaging over the one-step futures of epsilon neighbors from the input sequence. Now, this algorithm is from '87, but actually it uses a principle which is called nearest neighbor prediction. Basically, you want to predict a phenomenon, you have some data, you say, okay, I will take my data point, which is the closest, and this will be my guess. So this is a very simple idea, very straightforward idea, and it turns out that it was published for the first time over than 1,000 years ago in a book by Al-Hazen. But the novelty in their approach was that they used this idea in the time delay framework. And obviously, if you look at the literature, this is a very simple interpolation. You can do other things here, right? You can do very advanced interpolation, depending on the problem. Okay, so now this, I think, will explain why the authors of the paper I mentioned before define the following quantities. So we have, I will denote by HKT the time delay map of length k, and I define the epsilon estimate of the one-step future of I in the support of the push forward of the measure into the model space in the following way. So this is just an integral way of writing what we just described in the empirical algorithm. You fix some epsilon, you have this y, you look at the pre-image of this ball, you look at all x in this, you take their future, and then you hit with the time delay map, you take the average, and you normalize. And obviously, because y is in the support, this is non-zero. So this is the theoretical expression which corresponds to the algorithm. And they go further and they define the epsilon prediction error, which is associated with this procedure, just like you define the standard deviation. You see, you take the distance in this ball, squared, and then you take the root. And the prediction error for y will just be the limit of these quantities, right? Because we had this parameter epsilon, so we take epsilon to 0. Obviously, from a mathematical point of view, we need to ask, does this limit exist? So the system is said to be HKT predictable if with respect to the push forward of the measure, with respect to the time delay map, almost all y in RK have that not only that this limit exists, it's 0. So the prediction error is 0. So by this I meant that maybe if you see this definition for the first time, it's not clear why the authors would call this predictability. And okay, so we understood that it comes from this algorithm, but actually our first theorem was really to completely demystify this notion, which is not explained in the paper, in the original physics paper. So here is the statement. Let X be a compact set, mu a Borel probability measure on X, and T is a continuous map. Let H be a continuous observable. Then the system is HKT predictable if and only if there exists a Borel set of full mu measure such that for every x1 and x2 in this set of full measure, if both of them are mapped to the same point in the modeling space, so they have the same image under the K delay map, then the same is true for their futures. If you think about it, this is a necessary condition for you to have a prediction map in the model space. If this doesn't hold, there is no chance, because in the model space you have no idea from which x you came. So if it's possible to come from two different x's and go to two different futures, there is no prediction map. What is interesting is that this is an if and only if condition. The necessary condition turns out to be a sufficient condition in the probabilistic setting. Equivalently, so this is part 2 of the theorem, so if and only if, there exists a map in the model space to the model space. Actually, okay, I will not get into the technicality why I put here an x and here an xh. But the point is that there exists a prediction map in the model space that makes this diagram commutative. You can either go in the original system, where the future is given by T, or you can go to your model space and there exists a prediction map. And of course, the prediction maps of hx up to htk minus x must be htx up to htkx for mu almost every x. So I think this demystifies completely their definition, and this is non-trivial, right? Because it says that this intuitive notion of prediction is the same as what they defined in the paper, which was that the prediction error is 0 almost surely. Okay? So now in order to state the first conjecture, I need a little bit of more background. I need to define natural measures and information dimension. So we have M is a compact Riemannian manifold and T from M to M is a smooth diffeomorphism. We call a compact T invariant set in M an attractor if it has a basin of attraction. That is a neighborhood. So it contains an open set which contains this X, which is characterized by the fact that all points in this neighborhood, when you go forward in time, they go to X. So they can become closer and closer. And now we assume that we have something which is called a natural measure. So this is a concept that physicists really like. It is a measure which has the following property. For almost every x in B, with respect to the volume measure of M, for every continuous observable, we have that the time average converges to the space average of the observable, the continuous observable. Now, those of you who are familiar with the Birkhoff ergodic theorem, this is not the Birkhoff ergodic theorem, because notice that it's with respect to the volume measure. So this makes mu a very special measure. It's some interaction between mu, which is, think about it as a measure on the fractal, on, let's say, on the Lorentz system, and the volume measure of the surrounding Riemannian manifold. So actually, from a mathematical point of view, there are many open questions related to natural measures. It's not known when they exist. There are no, usually we don't have a good criterion to show that they exist in examples that interest us. So for us, it was a big problem that the original conjecture just assumed that this natural measure exists. But you will see that fortunately we were able to circumvent that. Another notion that appears in the conjecture is the information dimension. So information dimension is another dimension used in fractal theory. It's less popular than the Hausdorff dimension. It's more popular in signal processing. But it became very popular, I think, in the 80s in the literature about reconstruction, because they had algorithms that estimated very well. And it's defined in the following way. You fix some radius r, you take log of mu of bxr for all x, and then you take the average of this log. This is a negative quantity. You normalize by 1 over log r, and you take the limit. This limit, of course, doesn't necessarily exist, so we need to talk about upper and lower information dimension.
So, sorry, so this is a kind of a, this is a ergodicity, right? Ergodicity.
No, the natural measure doesn't have to be ergodic. I know it's...
Yeah, I missed it for toilet fire, so yeah,
are you asking about the natural measure?
No.
Okay, I understand your question. No, this is... I understand, because obviously we know that if we have an ergodic measure, mu, then almost surely with respect to mu, such a thing holds. But this is something else, because it's for almost every x with respect to the volume measure. So think about the Lorentz attractor, some fractal that has its measure lying inside a manifold, and you have this basin of attraction, because you see this is very important from a sampling point of view, because when we are doing an experiment, usually we are not on the attractor. We are in the vicinity of the attractor. So if we want to calculate some empirical averages and claim that these empirical averages go to the right thing, we want to have the tool that we can randomize our starting point with respect to the volume measure, which we have, and not the mu measure, which we don't have. That's the point. So to have a natural measure is very important from a point of view of an experimentalist. Maybe I should have said that. So it's a great notion, that just the problem is that from a mathematical point of view, it's very hard to show that you have such a measure. Okay, so one last more background, I want to touch briefly on prevalence. So we have already talked or mentioned genericity. In topology, a generic property is a property which holds on a residual set, a set which contains a countable intersection of dense open set. And prevalence is an alternative theory of genericity, which is more measure, has a flavor of measure theory. In some sense, it's the analog of almost sure statement in finite dimensional spaces. So here's the definition. Let V be a non-linear space. A set S is called prevalent if there exists a compactly supported probability measure mu, such that mu almost every E in the probe space, which is just defined to be the support of mu, and for every V in V, V plus E is in S. So basically, you start with any element in your linear space. You are allowed to perturb it with almost every element in your compact probe space, and you want that this perturbation will be in S. Then you call S prevalent. S is very big. And actually, we have seen an example of this in the statement, but the archetypical simple example of such a phenomenon is, let's say you have a Hilbert space and you fix some finite orthonormal set, and you consider the cube generated by it, as I wrote here, and you just consider the Lebesgue measure on it. So that's an example of a probe space in a Hilbert space, which is infinite dimensional. So it allows you to say prevalent statements in infinite dimensional spaces. And now I think I can state the first conjecture of Schroer, Sauer, Ott, and Yorke. The conjecture didn't specify everything. So let x b mu t be an attractor with natural measure, and h is an observable, then generically in the system, and basically they didn't say what they meant by generically. If k is bigger than the information dimension of mu, then the system is predictable. So they conjectured, this was based on their simulations in certain famous attractors. They conjectured that the information dimension is the important quantity, and if you take a window that is bigger than that, then the system will be predictable. Obviously, you need to do here some perturbation, so they say generically. So let me now state our first theorem. So let X be a compact Riemannian manifold, and let T be a CR diffeomorphism with an ergodic natural measure mu. Let K be bigger than the lower information dimension. So they assume that the information dimension exists. Here we don't need it, we just say that K is bigger than the lower information dimension, that obviously always exists. Then for a prevalent set of Lipschitz observables, the system is HK predictable. Notice that they said, they didn't specify, but it's generically in the system. Here we don't need to perturb the dynamics. We only perturb the observable. And as you can see, more or less, we showed that their conjecture is correct with one caveat. We assume that the measure is ergodic. So is this necessary? Can we get rid of this? So here again is the conjecture. And also, returning to something I said before, do we really need this smooth setting? I mean, as we said, most systems are not smooth. The phase space. So yes, you can generalize this. So let X be a compact set, mu an ergodic Borel probability measure, and T a Lipschitz map. Assume that K is bigger than the lower information dimension. Then for a prevalent set of Lipschitz observable, the system is HKT predictable. So as you can see, here we got rid of the smooth phase space. We got rid of the natural measure assumption. So this is key. It turns out that this was not, it was a red herring. There was no need to assume that the measure is natural, which, as I said, is a big theoretical complication. This works for every T-invariant measure. But again, you see, very annoyingly, we need to have this assumption that the measure is ergodic. So can we get rid of that? Because it didn't appear in the original conjecture. Yes, it's possible to get rid of it, but you need to pay a certain price. The same theorem is true for any T-invariant measure mu, no ergodicity assumption, if we use the Hausdorff dimension instead of the information dimension. Okay, so that's interesting. We don't need ergodicity, but we need to replace the dynamical quantity. So can you get both of them? Can you get rid of the ergodicity and also keep the information dimension? It turns out that no. We were able to construct a counterexample. So there exists a C-infinity smooth diffeomorphism of the three-dimensional compact Riemannian manifold, which is very simple. It's a product of the two spheres with the circle, with a non-ergodic natural measure mu, which has information dimension. It's well defined. It's strictly less than 1. However, its Hausdorff dimension is 1, such that for a prevalent set of Lipschitz observable, the system is not H1 predictable, right? The conjecture in this case, because the information dimension is strictly less than 1, predicts that it should be H1 predictable, but it's not. So I think this closes completely this conjecture. You can raise another objection, and that is there is a very famous open conjecture that is wide open by Farmer, Ott, and Yorke from '83, so many years already open, which says that for a typical attractor with natural measure mu, all the quantities that I mentioned are equal. So the lower and upper information dimension are the same, and they equal the Hausdorff dimension. So if this, now in the conjecture they didn't specify what they mean by typical, but probably it's in the same spirit of the result that we saw, so some prevalence result. So if this result is correct, this will tell you that actually in a prevalent sense the original conjecture is also correct. But as I said, this conjecture is open. Okay, so now let me move to the second conjecture. So here I just remind the definition of the epsilon estimate, epsilon prediction error. And as I said, the second conjecture, which I call the prediction error conjecture, has several cases. I will just focus on the main case. And it says the following. So you have a smooth diffeomorphism of compact Riemann manifold with a natural measure mu of information dimension d. You assume k is bigger than d. You fix a generic observable and sufficiently small delta, which we will think about as a threshold. Then for sufficiently small epsilon, you have the following. The measure of points where the error is bigger than your threshold has the following inequality. So it's less or equal than c times epsilon to the power k minus d. This is something they just extrapolated from simulation. It's very interesting. So this also explains the original title of the paper, which was, if you remember, predicting cows most of the time. What does it mean most of the time? What they mean is that in this sense, for most initial conditions, and as we know, if we have an ergodic measure a time, so a time statement and a space statement will be equivalent. So for most initial condition, in this sense, the error of the prediction algorithm will be smaller than our threshold, and even they give this very specific asymptotic, where you see the parameter epsilon, which is used in the algorithm to predict, to the power of the difference between the length of the window and the dimension of the measure. We were able to prove a version, let's say, of this conjecture, but we had to use a quantity which is the upper box dimension. So this is actually a topological quantity. It's not a measurable quantity. You cover your space with balls of radii delta. You consider the minimal number of balls in such a covering. You take the log and divide by minus log delta, and in this case you take the lim sup. And our statement says that if X is a compact set, mu is an invariant Borel probability measure, T is a Lipschitz map, upper D will be this is important, the upper box dimension of the support of mu, and we have a K which is bigger than this overline D. Then for a prevalent set of Lipschitz observables, for every delta and theta bigger than 0, there exists a C and epsilon 0, such that for every epsilon smaller than epsilon 0, a similar statement holds. The measure of points where the epsilon error is bigger than our delta threshold behaves as C times epsilon k minus overline D minus theta. So think about this theta as a very small parameter. So it's more or less the same form as in the conjecture. However, The big difference, so it's a weakening in this sense, is that we don't use a dimensional quantity of the measure. We use the topological dimensional quantity of the support of the measure, and this can sometimes give you a jump. So this is what we were able to prove. Now I have 5 minutes, so let me, I wanted to give you some elements of the proof of the first theorem. In order to simplify even further, I wanted to give the proof of the a non-dynamical analog of the probabilistic Takens theorem that we proved, which is the following. If we have a Borel set equipped with a probability measure mu, and we know that its Hausdorff dimension is strictly less than d, and we have phi, which is a locally Lipschitz function, then for Lebesgue, almost every linear transformation from Rn to Rd, there exists a Borel set of full mu measure such that when you take this linear perturbation phi plus L, it will be injective on XL. In order to make this very clear, this actually will tell you that for Lebesgue, almost every d-dimensional linear subspace, so imagine you have this set, it lives in a very high dimensional Euclidean space, but you know something about its Hausdorff measure, and you start considering the projection of your set on some randomly chosen d linear subspace, where d is much smaller than n, then the orthogonal projection will be injective on a subset of full mu measure. Okay, so here are really an overview of the proof that will give you some feeling of how you prove such statement. We consider the linear transformation element of R and D. Here I just switched, I called the space X prime, and then I switched to a subset X, which has full measure and has the Hausdorff dimension less than D. And then the key object, let's say, is the set A. This is a set living in the product of X and the space that parameterizes the linear perturbation, just that we take now linear perturbation living in the unit ball. And you take bad pairs. What are bad pairs? These are pairs where there exists some y, which is not x, such that phi Lx equals phi Ly. So it's bad because it destroys the injectivity that you are looking for. And then one can consider the sections of this bad set. Ax will be the L's, such that x, comma L is in A, and Al will be the x, such that x, comma L is in A. And then our goal will be to show that for Lebesgue, almost every L, there exists a Borel set of full measure such that x, comma L is not in A. This is a little bit stronger than what the theorem says, but if you can prove it, it implies the theorem. And here we just use the idea that we can use the Fubini theorem. So instead of showing this by Fubini, it's enough to show that when you consider the other section, it has measure 0. So I don't know, we think about you have some set here, and instead of showing that almost all these vertical lines have measure 0, you show that all horizontal. That's a very simple idea. It's of course enough to show it for almost every x, but we will just show it for every x. We will show that this section Ax for every x has Lebesgue measure 0. This is very useful because now we can forget about our original measure that we don't know anything about and work with our very familiar object, the Lebesgue measure. And so what we do, we just write our Ax as a countable union of sets, and because I don't have much time, I will just say that we use the definition of the Hausdorff dimension, and then we use the fact that we are in the bad set in order to estimate some distances. Then we use some geometric lemma. So because we are in the Euclidean space, we are using the Lebesgue measure. We have this tool, a simple geometric lemma. We apply it, and we get the estimate. So I'm sorry I couldn't give all the details, but I think more or less maybe it can give you an idea. I should say that the converse result, the reconstruction results, they use a completely different technique of proof, but maybe this gives you a feeling of at least one proof. Thank you very much.